When you finish moving DC voltage and current sources and simplifying the biasing network, you will end up with a circuit which has just a limited number of current sources that cannot be moved anymore. These ones are typically current sources that have one terminal connected to ground or connected to VDD, and DC voltage sources that have one terminal connected to ground, that are typically voltage references or the power supply. Okay, so at the end you will have to implement these sources with the transistors, and then you will do that by using current mirrors or other circuits that we have discussed during the lecture. So I have the same circuit here in which we have replaced this current source by a current mirror. So we have our current mirror here. Let's see if we can highlight the nets. Okay, so we have a current mirror here, and then we have the tail current. Also we have created a current mirror for the tail current here, and from the same current mirror I am deriving also the DC bias for the output stage. So we have another current mirror. So the three current sources have been implemented using current mirrors, and for that I have a current reference that in this case I just set for 2 microamps. I could have probably done it with a much lower current. And then I am just mirroring this current to generate the current reference that I want. So I need another branch to generate the PMOS current here. So I am mirroring the 2 microamps here to 2 microamps, and from this one I am mirroring and generating 10 microamps, changing the sizes of these transistors. And what is important here is just basically to make sure that when we create these current sources, they have enough output impedance and that they are not contributing with too much capacitance. Another extremely important detail, it is that when we put the transistors here, we put the current mirrors. Due to the capacitances, there are going to be capacitive coupling between the output. For instance, here we have the output node is going to couple capacitively to the current through the current mirror to the gate, and then it is going to be connected due to capacitances also to other parts of the circuit. For instance, to the differential pair, the sources of the differential pair is coming here. The output will be also coupled through the current mirror. Here it is going to be also mirrored back to this point. So I have an intended feedback that it is introduced due to the presence of the current mirrors. And to break these feedback loops that might change the stability and change the dynamics of the loops, what I do is I add the coupling capacitors. I am to ground. So in the case for the NMOS current mirror, I add one capacitor to ground here, so that it is basically at high frequency shorting to ground the gates. So in that way I break the loops. So there is a mitigated the crosstalk that exists between the output and the gates. For the PMOS I have to do the same, but then I put the coupling capacitor from the gate to the power supply. So then basically at high frequencies I am shorting the gate and the power supply. That it is about the very important detail. These the coupling capacitors also help me to filter high frequency noise. So there may be noise coming from the current reference here, and then I am building a low pass filter also with this capacitor. The same here. Remember that the current mirror is extremely noisy, so I can benefit from the presence of these capacitors because they act as low pass filters. Regarding the voltage reference that I needed, typically there are in a chip there are several voltage references available that are derived from a bandgap reference, that it is a very stable voltage reference that keeps a relatively constant value over process and temperature variations and voltage power supply variations. So there are the voltages normally that are derived from the bandgap voltage references. So we can tap in one of these ones for the reference that we need, around 900 millivolts. If that voltage reference is not available in the chip, we might need to derive one ourselves, voltage reference, and then we can use one of the circuits that we have studied. In this particular case, I use one that it is very simple. It is just diodes. We have diode connected transistors in a row, so they are working basically like a kind of a voltage dividers. So I can tap in the one voltage that it is closer to the voltage that I want, and I have also a large capacitance that it is shunting that node to ground. So that is important because there will be also noise that it is coming, and then we need to filter that noise to ground, and we need to reduce the impedance also. Remember that the voltage reference, voltage source has to be low impedance, so I reduce the impedance by placing a capacitor to ground. Okay, so there are implications of using this structure. It is basically that any variation in the power supply will immediately be seen in the voltage reference, which means that it has a really poor power supply rejection ratio. So even small variations on the power supply here will change this voltage reference. So it might have an impact in the performance of the circuit if it is sensitive to that. So we're going to do some simulations of this so we can take a look what is the impact of the power supply. So this is one of the options. We have actually another alternative. So as I mentioned before, the differential pairs can be implemented using active loads in the form of current mirror loads. So this is exactly the same circuit. Everything it is the same. The only difference is that this circuit has a current mirror load, and I think only the devices are slightly different. This has 20 micrometer and length 1.5 micrometer, and this has 16 micrometer and the length of 1. So it's not so different. So, but the main thing that we can see here is that we don't need another current mirror branch in order to generate the 10 microamp here. So we get rid of that current mirror branch, but the circuit behaves slightly different. There is one pole that appears here because of the presence of these transconductance and capacitance here. So we might have a slightly different frequency response that we might need to adjust also for the stability. And the other thing is that the noise performance is different. The noise performance is different, and then we can explain by looking to this circuit here. For DC, we have that the tail current, this tail current, it is divided by 2. Okay, so we have half of the current going to transistor M0, half of the current to transistor M2. Well, it happens exactly the same with the noise. The noise generated by M5 it is going half to M0, half to M2, and it will basically appear or propagate directly to the output without any attenuation. Another important thing it is that all the noise of M8 also will propagate directly to the output. So we have and also, I mean, it is a current mirror. We have that also. We have to be careful that noise from the current mirror will not be amplified by M8 will appear at the output. So yeah, there are the consequences of using this kind of circuit. Now the other implementation with the current mirror load has the following characteristics. No? So if half of the noise is coming to the left and half of the noise is coming to the right, it happens that this noise here, it is basically mirrored here, and then it comes back, but with another phase, with this 180 degrees. So it basically subtracted here at the output, which is something it is something very positive. So the noise of M5 does not propagate. It is we will run some simulation to see that it has a little bit better noise performance because of that, and the biasing is of course simplified. So at some point you are done with the circuit and you need to run a set of tests to make sure that everything it is as you expected. We're going to run very quickly a last simulation with ADEL before we go forward and run a set of more advanced tests over our circuit.